Hello and welcome. In this video, we're going to introduce the next topic in our next unit, and that is thermochemistry. So, it being an introduction, we're going to talk more about some basic terms, concepts before we get into greater discussions on calculating exactly how energy moves from reactants to products or reactants assist to the system to the surroundings. Um, let's start. So, this being a chemistry class, we're going to focus on changes in energy that occur in chemical systems. So chemical changes, we will definitely talk about physical changes as well. Mention that over here, right? A change in state, say from a liquid to a gas, means that kinetic energy between these molecules, let's say ice to liquid or liquid water to water vapor, essentially that is a change in energy, change in kinetic energy that increases intermolecular forces. Let me rephrase that. That will increase the intermolecular attractions between these molecules, breaking some of these intermolecular forces and changing state. Um, we will focus mostly, however, on chemical changes and chemical systems. We're going to see how energy can travel from a reactant to a product or from reactants to surroundings. And these terms we will review, endothermic and exothermic, we will review right now or shortly. First, though, some definitions. So a system, you can think of it as, all right, I'm going to attempt to draw a flask. All right, so a system is anything that is inside the chemical reaction that is happening inside of your flask, right? Surroundings would then be on the outside, right? So all of the surroundings on the outside. System is on the inside. Now, an open system is one that will allow material to escape a flask, right? A closed system would just mean that you have stopped this. A rubber stopper is on this flask and material cannot escape, right? It cannot escape. It stays inside, and that would be your closed system. Okay, so let's label some of these things, right? So this is a flask with a balloon over it. This would then be considered a closed system because it cannot leave. It's stopped by that balloon here. So this is an example of a closed system. You can see that in this round bottom flask here that it is an open system, right? These are both. This is system inside. Yeah, that round bottom flask. This is system inside that Erlenmeyer flask. This is open. We can see material escaping here, right? The surroundings are, of course, just anything on the outside. Surroundings, anything on the outside, right? Now, what is able to happen between a closed and an open system is that you still have a transfer. You still have a transfer of energy. So, energy can be certainly here, and it can be transferred between a system and its surroundings in an open system, and it can still be transferred between your system and your surroundings in a closed system. Remember, material can't in a closed system, but energy can. Okay, now we measure thermal energy in the form of temperature. So temperature is what we use, or thermometer, say, is what we use to measure um, thermal energy in the form of kinetic energy. So the energy held within or between molecules, right? Now, what is key here is this. So heat doesn't exactly mean thermal energy. Heat refers to a movement of this thermal energy. So the flow of thermal energy between substances or to the surroundings. So once energy is moving, that is what we say is heat and refer to as heat. Okay, so here's a bit of a discussion then on a bit of physics. You know how much you like that. So to calculate the total energy of a system, it involves two parts. Right, so it involves potential energy. Now, in physics, that just means changing perhaps a condition or the position of an object, right? So we have a potential energy of this weight attached to this pulley system. In a chemical reaction, what the equivalent of that, or rather in a substance, in a chemical, that is the potential energy is held within bonds, right? So anything that is, let's say, always go back to organic chemistry, and anything held within the energy held within these bonds here, that is potential energy, right? And breaking these bonds will then release energy. So this is potential energy held within these bonds. That's potential energy. Now, kinetic energy is the amount of energy that a substance will hold. between molecules, right? So between molecules. Okay, and again, this can be used to calculate. Rather, this can be calculated or measured, I should say, by temperature and a thermometer. Okay, so now there are different kinds. Then now specifically getting into chemical systems, there are specific kinds of chemical reactions. Now, one is exothermic. This is where reactants, after they react, maybe I'll start at the beginning though. So reactants have a certain amount of potential energy, and we measure energy in the form, and I think it's written here as joules or kilojoules. We measure right in joules or kilojoules. Now reactants have a certain amount of potential energy held within their bonds. Now, for them to react, even for something that's flammable to react, you need a spark or some heat, something added for that reaction to actually take place. So that's called your activation energy, right? Activation energy. We'll talk more about what an activated complex means. We'll have a lot of get into that in quite a bit of detail, but for now, we'll just leave it as a state between reactants and products. Okay, that's all you need to know for now. Once it is able to react, you have an activation energy that causes the reaction, a spark, heat. Then, when it's finally reacted, we see that the amount of energy that products have, right, is less than reactants. And this difference, which we will spend a lot of time calculating, this difference is called enthalpy, or a change in energy, called enthalpy. Okay, so between the products and your reactants. Now, what that means is this energy was lost. So this was lost to the surroundings, right? From reactants, it was lost to the surroundings. The next kind of reaction is an endothermic reaction. So here, again, we're measuring potential energy within bonds. Reactants have a certain amount of energy. Now here we need to apply perhaps even more of an activation energy so that the reaction takes place. But once it does, what we end up with is products that have more energy than their initial reactants. Again, all held within their bonds. Right? And this difference between reactants here and here, this time it's energy that this energy is not lost to the surroundings. Instead, energy is transferred. This energy here is transferred to products. Right? So now your products have more energy than your reactants did. Right? So it's absorbed some of this energy. Okay. We'll save this from when we're in class, hopefully. All right. So the difference then the difference enthalpy in energies between reactants and products, those can have negative and positive values. Right? A positive value means that it is like endothermic, which means that your reactants gave energy to your products. And your enthalpy value, therefore, the difference between energies of these two, your reactants and products, is going to be positive. It started off at, we're going to make up some arbitrary numbers here. It can be 10 kilojoules, and your products could then be, let's say, 20 kilojoules. So that difference was a positive difference. Okay, not the case though for an exothermic reaction. Just erase all this. Okay, not the case for an exothermic reaction. In an exothermic reaction, we have energy lost to surroundings. So when enthalpy is negative, oh, do these. Right, when enthalpy is negative, it's going to be endothermic. So let's say these reactants lose energy to the surroundings. Right, and this energy is lost. Right, now if you think of the difference in between products and reactants, we can say again, let's use this a similar analogy. We're going to make something up. We have 10 kilojoules, and let's say our products have 5 kilojoules. So that difference then was loss, right? Surroundings gained those 5 kilojoules. Surroundings gained it, but the system that we're talking about here, the reactants themselves went from 10 to products, which is now 5. So it's a negative enthalpy change. Here's an example then of a brief explanation on how exactly ice melts in your hands and how this flow of energy occurs. So in this picture, we can see that, well, you can't see, but you can certainly see a change in phase here. What's happening is energy in your hand, assuming your hands are warm, at least warm enough to melt this ice, energy from your hands is being transferred, right, to that ice, to the ice cube. Now, what's happening in these ice cubes is that little water molecules, they're beginning to move around faster. So we get kinetic energy increasing. And as they move around faster, it's breaking those intermolecular forces, those intermolecular bonds, holding them in this solid state, changing it therefore to a liquid state. In other words, it's melting, right? So this energy then is moving from your hand into ice. So if we look at the system here, just this ice cube, and we make up some arbitrary numbers. Let's use these again. So I always write that. No, it's 10. Let's say, just to say 10. 10 kilojoules, and now it is, let's say it's gone up to 20 kilojoules. This is a positive change, so it'll be a positive enthalpy value. So this is an endothermic, don't want to say reaction because it isn't a reaction, it's an endothermic delta H positive value. Okay, now this is a physical change. This is now a chemical change. Now your propane or your methane being used in a barbecue, the potential energy held within the reactions or within the reactants, your combustible here is greater than the products. And what's happening is that this energy is being lost to the surroundings. The surface of this grill, therefore, and its surroundings are hot. Now all that heat, all that energy, I keep on saying heat and I shouldn't refer to all that thermal energy, which was held within those chemical bonds is being released, then transferred as heat, and you will cook something on, let's say, this grill because of that. Okay. Without getting into the physics, I can refute this entire slide here. Energy is in a system, at least, is constant. It can't be created or destroyed. Right? You learned this in your physics classes. Um, we're going to continue this idea. All the energy that's held within the bonds of a reactant can then move into the surroundings or can be transferred to products. Okay, and we're going to calculate. We're going to work on calculating exactly what those numbers will look like. That is essentially it for an introduction to chemistry. We're not ready to begin talking about that delta H, right, that delta H value. How can we calculate that? There's several ways we're going to look at in this unit before we get to the kinetics portion of this unit. All right, don't forget, ask questions and practice what's posted here.